Hi students, welcome back. Today we are going to look at the binary tree level order traversal problem. So this one has applications in many other problems and it's good to learn this in detail. So let's get started. So what is the problem statement? We are given a root of a binary tree and we have to return the level order traversal of its nodes. And the traversal should be from left to right, level by level. Okay. So let's see an example. So in this example, we are given a binary tree which is represented in the below graph like this. Okay. So what we are supposed to do is we are supposed to return this level by level. So how is level defined? Root is one level. Everything under root is another level. Everything below that is another level. So if you see, the output is 3, 920, which is the next level, and 15.7, which is the next level. Okay, and it is a list of lists. So we are basically uh, reading level by level and returning it. So there is another variation of it. It can be a single list as well. You basically return it like this. Okay, which means the output would be a single list, which is 3, 9, 20, 15, and 7. So both of them need level order traversal. It's just the way you are returning is different. One is a single list and the other one is a list of lists. Okay, let's look at another example. So here if the tree has only one node, obviously you will return only that, but it should be a list of lists. Okay, and if the tree is empty, your output is empty. Okay, so let's look at the algorithm with an example. So let's use the same example that is given. Like we have discussed before, level order is figuring out level by level. So for level order traversal, breadth first search is the way to go. So breadth first search will do the breadth, will search the breadth first, which is will search it level by level. Hence, when you are doing level breadth first search, if you capture the nodes, that is good enough. So for breadth first search, what is the data structure we need? We need a queue. Okay. So let's say we start with a queue and initially we will add root to the queue. So initially the queue will have 3. Now what we will do is while queue is not empty, okay, while this is not empty, okay, we will pick all the elements out of the queue. So currently there is only 3, okay, and we will add it to a, so that the current elements in the queue, that is nothing but a level, the current level. Okay, so we will just pop all elements and add all children to the queue, all children. Okay, okay, this popped elements is nothing but level. Okay, we will add this level to the result. Let's say we have something called result. We will add this level to the result. Okay, so let's see how this works out in the current example. So we have 3. So we have to pop all the elements. So let's say our result array is like this. Currently it's empty. So we have to pop all the elements and add it to the result. So this is what the result would be. And we have to add all its children to the queue. So what are all its children? 9 and 20. So we have taken 3 out. So 3 is no more in the queue. Okay. So in the next iteration, what we will do? We will add, we'll pop all the elements and add it to the result, which is 9 and 20. And next, what will we do? We popped all the elements. So these are out of the queue. We will add all its children, all the children of 9 and 20. Here 9 doesn't have any children, but 20 has 15 and 7. We will add them to the queue. Okay. Then in the next iteration, we'll pop out whatever is available in the queue, which is 15 and 7. we will add its children to the queue. But both 15 and 7 doesn't have any children, so we have nothing to add. At this point, the queue becomes empty and we just return this result. Okay. So we are basically using the queue to keep track of all the children of the current level. Okay. Let's write code for this. So in the problem itself, we are given this tree data structure already. So we are given a tree node which has a value which has a left child, right child. So to the problem, the input is directly the root which is represented by that tree node. Okay. So let's, so for this problem, what we have to do is we are doing BFS, so we need a queue. So let's initialize a queue first. Okay. Queue interface is implemented by linked list, so we are using that. And we also need a data structure to store the result. Result is list of lists. Okay. So let's create result. Okay. And finally, initially, we have to add the root to the queue. Okay. So if once we added root, okay, as long as the queue is not empty, okay, what will we do? We will create another list called, okay, each row, or we can even call it level. So each level. So we will pop all the elements of the queue and add it to this list, which represents the current level. Okay. So to pop all the elements of the queue, we need to know how many are there in the queue currently. So let's take the queue size. Okay. So we will do, we will keep removing from the queue as long as the size to that size. Okay. So let's get the current node. Okay. Right. Then what do? We have to add it to the current level and we have to add its children to the queue. Okay. So, but before doing that, we have to check if the node is null. If node is null, we don't have to do anything. Okay. Otherwise, we have to add the node current node's value to the level and we have to add its left and right child to the queue. So we could have just popped until the queue is empty. Why did we take size here? Because we are also appending to the queue. So we should know what is the size of the current level before starting this process, which is why we have to capture the current size first. Okay. So we have the level and we have added it to the list. Now, in some cases, the level can be empty, right? Like the test case where the entire list is empty. So we have to check if level is greater than 0, only then we have to add it to the result. Okay. And finally, we have to return the result. Okay. Let's run this and see. Okay. Let's submit it. Yeah. And how do we figure out the time and space complexity? Here we are taking an extra data structure here, which is order of n. Okay. It can maximum, it is basically order of size of the each level. But you can assume which can be maximum of n by 2, which is nothing but order of n. Okay. And this result is it won't count under space complexity. It is just required to return the result. And as long as the queue is not empty, we are traversing each node in the list. We are touching each node at least once. So the time complexity would be order of n. Okay, so the time complexity is order of n and space complexity is order of n. Okay, so this is when we return list of lists. Okay, now what if we want to do the other version where we just return the um, linear list instead of list of lists? So what change should we make for that? You can take that as homework. You have to make very simple modification here to get that output. Okay, thank you for joining. Hope you enjoyed the video. Please like, share and subscribe.